So my today's topic in the second session is on the evaluation of statistical parameters uh, of the probability distributions, where I have considered two special types. One is called Poisson, another is called binomial. Now, you may ask me that this particular chapter has already been done. We have evaluated parameters, statistical parameters. But if you can recall that while discussing this particular topic, we just did some sort of calculations. I gave you problems and I asked you to find the mean and variance, and if it is a case of binomial distribution, we found the number of experiments and the probability of success, etc. and etc. But I'm not talking about this. I'm talking about something else right now. I'm talking about a kind of function which is which helps us to generate the expectation and variance of a particular random variable. Such a function which I'm going to discuss right now is called the moment generating function of a random variable capital X. Before I scroll down further, I have to tell you something about moment generating function. Now, this thing is a little bit of this understanding is requires a little bit of attentiveness. So listen to me very attentively, and it actually is not that easy as people can always think of. You have to give a little thought on that. We are studying a system, and the system follows a kind of probability distribution. Maybe we know the probability distribution, and maybe we do not know it. If we know the probability distribution, if the system is such that it is actually following a probability distribution from our known domain, then it is all right with us. But if the situation is like that, the system follows some sort of probability distribution, but we do not know what is it. It is not binomial, it is not Poisson, it is not uniform, it is not a negative binomial, it is not normal. What is it? I don't know. So in that particular case, we have to first give some effort, some considerable amount of effort to find the probability function of that particular random variable associated with this unknown system. Once the probability function is known, then we become interested in finding the mean of the random variable and variance of the random variable. And we know from one of our earlier discussions that this mean of the random variable and variance of the random variable can be calculated from moment. Moment is the general term which contains in it mean, variance, and other things like expectation of the random variable cubed or expectation of random variable raised to the power 10, etc., etc. As much as you can elongate it, as much as you can raise the power. So all these are confined in a particular entity which is called moment. Now the question is, if the moment is known, if the moment of the random variable is known, then we know already that we can find the expectation and variance of the random variable. But can we find the moment at all of the random variable? How can we find the moment of the random variable? That is our today's task. And we are going to get to know what is moment generating function. By its name, we can easily understand that we are going to discuss about a function which helps us to generate moment of different probability distribution. So the technique which is there in the note gives you an idea about how to generate moment generating function, or how to obtain the moment generating function of some known distributions. In this particular case, I have taken the case of binomial and Poisson. First of all, you have to understand the definition of moment generating function. So moment generating function of a random variable is defined as follows. We denote this by mxt. Here in the suffix, we have written capital X, which tells you that the associated random variable capital X, and we have considered a variable small t, which is input variable. Now that is equal to expectation of e to the power tx. This is the definition of the moment generating function. Remember, this is not a mistake. Okay, I am intentionally writing it as capital X. The mother variable is capital X is being written over here because this is just an expression. It is not a calculation. In the calculation part, I have replaced the capital X by small x. And you know, if you can recall that expectation of capital X for discrete case, it is the value multiplied by the respective probability. But in place of capital X, we have this function, e to the power tx, e to the power t multiplied by the random variable capital X. So this definition has been used over here. Try to correlate the definition. This happens when X is discrete, and the summation is replaced by integration when X is continuous. Okay, so this term, expectation of e to the power tx, that is denoted by the notation mxt. By mxt, we actually mean it. Okay, it is just a notation. This is the definition. E to the power x is a well-known series. It goes like this. E to the power x can be written as 1 plus x squared by 2 factorial, x cubed by 3 factorial, and so on. Now, in this type of scientific calculator, you know, there is just above the logarithm key, the e to the power x is there, and if you want to calculate the exponent of something, we just press the shift button, and we directly can find out the value e to the power e raised to the power any value, any number. So you can find out e to the power minus 1.5, you can find out e to the power 2, etc. and etc. Okay, now as for example, if I try to find out e to the power minus 1.5 by the calculator, then the answer is coming out as 0.2231. And now suppose this calculator is not there with you, what will you do? You have to know the series. This series helps you to calculate the following value. Now what I can consider over here, this series is an infinite series, but obviously our space is finite. Even if I want to write the algorithm and our computer program to calculate the e to the power x, and you know this is a mini computer, so they are not actually considering the entire infinite series. They are considering a few terms only. I do not know how much term they are considering, how many terms they are considering. So if you want to say calculate roughly e to the power minus 1.5, we can take the help of this particular series. And if I consider only 3 terms, e to the power minus 1.5 can be written as 1 plus minus 1.5 plus minus 1.5 whole square by 2 factorial. So the value which will be obtained will be an approximate value. It may not be equal to 0.2231. It is a matter of checking to know how many terms must we consider to get 0.2231, and it is a matter of numerical calculation, numerical analysis. So we are not going to discuss about it. Why I am considering this particular series e to the power x? Because in this moment generating function, you can very well see that e to the power tx type of thing is present. Now, if we know this particular series, then we can take the help of it, and we can write e to the power tx as follows. So in place of x, we have tx. So we are replacing all the x's by tx's over here. And in this manner, we are getting e to the power tx as 1 plus tx whole square by 2 factorial plus tx cubed by 3 factorial. And if you want to write a general term, tx whole thing to the power r by r factorial. Okay. Why am I so much interested in writing this particular formula? Because since we know that moment generating function is this, and it is given in terms of expectation, so at least in place of this value, we can put this entire series and you can calculate the thing item. This is a very well-known theorem, but I'm not going to prove the theorem. You can do it by yourself if you want. you can take the help of mathematical induction in this particular case, that when mxt is present, mxt is there, you can take the derivative of this function mxt, r times derivatives, and you can put at the value, at the point t, its value to be 0. If you substitute that, then you can easily calculate mu r prime. The result which you obtain is actually equivalent to mu r prime. So ddr of mxt at t equal to 0 gives you mu r prime. You can prove it if you want by with the help of mathematical induction, or you can take simple examples and you can check it. What is mu r prime? If you go to my earlier note, you will find that mu r prime is the moment about origin. Okay, so if the moment generating function, the theorem says that if the moment generating function is known, you can easily calculate the moments with the help of the given formula. Now let us elaborate the moment generating function in case of discrete case a little bit. We already know that mxt is given by this formula. We have substituted the series in place of e to the power tx already. And now I'm operating the summation on each of these individual terms. Now look at the terms. First term is coming out as summation fx over x, and we are considering all the possible values of x over here. So it is actually taking the total probability, which is equal to 1. Small t is the parameter. It is a constant quantity, which is independent of summation. Okay, it is independent of the summation x. So we can take t outside the summation sign, and inside we get x, summation x into fx. Similarly, from the third one, we get t square by 2 factorial x summation x square fx, and in general, t to the power r by r factorial summation x, summation over x, x to the power r fx. Now, you know that we have discussed that summation x fx is nothing but the expectation of x, and expectation of capital X, as you can see, if you can recall, that expectation of capital X is the first moment about origin. I already showed you in a note. Okay, so we can replace this summation x fx by mu1 prime. Similarly, we can replace summation x squared fx by mu2 prime, the second moment about origin, summation x cube by x cube fx by mu3 prime, and so on. And mu1 prime is actually equal to mu, because mu is by definition, mu is the expectation. By notation, we consider it to be an expectation. So we can replace in place of mu1 prime, we can replace it by mu. So it's just a notation. Okay. And we have written the thing once again over here. This entire calculation which has been shown to you, this blue colored portion of the node, can be replicated once again when the variable capital X is continuous. The same thing will come out, only the summation, in place of summation sign, the integration sign will be there, some limits will be there. Okay, nothing different will be observed. Same thing. And that is just for your prerequisite that we discussed that mu r prime was having the formula of this kind and that kind for two different cases. One is discrete and another is continuous. Actually, we have taken the help of this particular formula notation, and we have substituted it in the formula, in the expression of mxt. Now, problem number 1, I have taken the as a special case of discrete random variable, I have considered the Poisson distribution case, because we have already studied Poisson distribution, and we know that the probability mass function of Poisson variate is given by fx equal to e to the power minus lambda to the power x by x factorial, where x is lying between, x can take value from 0 up to infinity. You can ask me why have I taken this Poisson distribution in the first case. I have two answers for this. First answer is that Poisson distribution, the evaluation of its parameter, its moment generating function is there in the syllabus. So therefore we have considered it. Second argument is that if I take any unknown system whose probability function is not known, then I'll not be able to show you the moment generating function, because moment generating function requires probability function for the calculation. So I am considering only those distributions whose probability functions are already studied. So I am, as a first example, I'm considering the Poisson distribution. And you know the Poisson distribution's parameter is lambda, which is the product of the number of experiment and the probability of success, NP. And Poisson distribution is a special case of binomial distribution where n is too large and p is too small. Now here also there is a point that one student day before yesterday he called me and he asked me that in a particular problem he was getting the answer, the solution done by Poisson distribution and binomial distribution to be same, but he thought that it shouldn't be. So I gave him some sort of justification. And since you have not encountered such a situation, then I'm not telling you anything about that. First you encounter such a situation, then if you face difficulties, if you are overwhelmed by these things, you can ask me and then we can discuss. Okay, first of all, I want you to face the situation. Face it, then ask me, I will clarify your doubt. Now, moment generating function of the Poisson variate is given by mxt, which is this, and then I'm replacing in place of the probability function. Just let us have a look at the formula. The formula was like this thing multiplied by fx. Fx is the probability function. So here I am putting the fx, which is the Poisson probability, and e to the power tx remains same. Now what I'm doing, I'm not actually putting the entire series, because I want to get some sort of function in terms of the variable t. Okay, I'm not interested in the entire series. So what I'm doing a trick over here. E to the power minus lambda is constant quantity, which comes outside the summation sign. And you see, we have inside the summation e to the power tx into lambda. Both can be raised to the power x. So I am writing it as lambda e to the power t, lambda into e to the power t raised to the power x by x factorial. And I'm running the summation from x from 0 to up to infinity. We get this expression. Try to look at this. In the last semester, we discussed, although we couldn't discuss it in very well, okay, because for the lack of time, this was the thing known as the Maclaurin series, okay, of e to the power z. Now this series, which the series we have obtained over here, which has been multiplied by the quantity to the power minus lambda, you can say in correlation to that, it is the Maclaurin series of e to the power lambda into e to the power t. Okay. So mxt can be written as e to the power minus lambda, and you see this thing is e to the power lambda into e to the power t. Okay, this is the series. This is the exponent. If you put the values of x over here, first value will get 1. Second value will get lambda e to the power t to the power 0 by to the power 1 by 1 factorial plus lambda e to the power t whole square by 2 factorial, and so on. So actually it is the series of e to the power, it is the exponential series of lambda e to the power t. So I'm writing in place of this summation, I'm writing this. Now add the common powers, and ultimately we are getting mxt to be e to the power lambda multiplied by e to the power t minus 1, which is the moment generating function of the Poisson random variable. So which is given in equation number 1. Now by the theorem which I gave you above, that means this one, this is a very important theorem. So we are going to take the help of this particular theorem below. So what we have done over here is that we have taken the first derivative of the moment generating function, which we denote by mxt prime, which is d dt of the quantity of the expression. After derivative of this, we get this expression. Now, I'm not going to explain this because it is a matter of calculation. Double derivative when taken gives me this expression. In the theorem, it is mentioned that we are supposed to substitute t equal to 0 in the expressions after taking the derivative. So we have put t equal to 0 over here. And first derivative at the point t equal to 0 gives you the first moment about origin according to the definition, which I have explicitly written over here, which has come out to be lambda, which is expectation of capital X. So with the help of moment generating function, we have found the mean of the Poisson random variable, which is lambda. You already knew the result from our earlier discussion. Now we have directly calculated it. And similarly, here are some notes which have already been discussed earlier, just to recall you, just to make you recall, to help you recall the things. I have again put the things over here. And similarly, if you want to calculate the variance, we will take the double derivative of the moment generating function at the point t equal to 0. And further calculation will reveal that e of x square will come out to be lambda plus lambda square. And you know that variance of x is ex square minus ex whole square. So which is coming out to be lambda plus lambda square minus lambda square, which is lambda. And therefore, it proves that it justifies or verifies the fact that the Poisson distribution is a kind of discrete probability distribution whose mean and variance are same. Second problem, yeah, there is a printing mistake because the previous one was problem 1, so this should be problem 2. But this is pardonable printing mistake. Anyways, in the second problem, we have considered the binomial distributions case. In binomial distribution, you know the probability function takes the following form. Now, just like our previous example, we have considered the mxt of the binomial distribution, and I have substituted the probability over here in this manner. Little thought will reveal that this expression, this binomial expression, preceded by a summation like this, it's actually the quantity given by q plus p to the power t raised to the power n. You can just check it. You can put the different values. This is the xth term of the expansion. Okay, so this is the moment generating function of the binomial random variable. Similar to the previous example, we can calculate the first derivative of the moment generating function at the point t equal to 0. You will find that np will come, and second derivative of the moment generating function at the point t equal to 0 gives you n into n minus 1 p square plus np, which is ex square, and consequently the vx will be calculated as npq. Now, I am asking you to somewhere note down these expressions, like the moment generating function of the Poisson variate, which has this expression, then moment generating function of binomial variate, which has this expression. These moment generating functions of different probability distributions are often asked in competitive examinations. And if you have the moment generating function with you, and if you know that theorem, dr dtr of mxt at t equal to 0, if you know that theorem, you can calculate expectation of the any random variable, variance of any random variable according to your with respect to your system. But only requirement for finding moment generating function is to get hold of the probability function, which is very important. Okay, so I'll ask you, all of you, that so far we have discussed the probability distributions of binomial and Poisson. So you somewhere in your copy, you note down, you make a chart. Okay, so in the chart, your first column will be the names of the probability distributions you have studied so far. Second column, you write their moment generating functions. e into e to the power lambda e to the power t, lambda into e to the power lambda into t. That is the thing. What was the expression? See, I'm also forgetting. You have to recall it. Just a minute. Yeah, this is the expression. E to the power lambda into e to the power t minus 1. This is the moment generating function of Poisson distribution. And for binomial distribution, you have got the moment generating function to be this. You write it in the third column. Then the fourth column, you mention the mean of the two distributions. For binomial, it is NP. For Poisson, it is lambda. In the fifth column, you mention the variance. Also, you mention, if you can, the quantity Ex squared at least. And you keep on expanding your chart. Once you get hold of a probability distribution, immediately find its moment generating function, its mean, its variance. Moment generating function, its mean, its variance, and so on. If you can keep this entire chart in your mind, then in practical field or whenever it is required, that will be very helpful. Okay. And we often try to do so. Although I have forgotten, you can say that, sir, you are forgetting things. Yeah, I'm forgetting things a little bit. But you shouldn't be like me, isn't it? And here in problem number 3, I have given you something which is different. In problem number 3, I have given you a kind of probability function which has the expression like half into e to the power minus mod x. X is lying between minus infinity and plus infinity. I don't know what sort of probability function is what sort of distribution random variable is having this sort of probability function. The point is not about the random variable. Point is about the probability function. Probability function is known. Can we find the moment generating function from here? So they have, in problem, it is given that if the probability function is given like this, moment generating function can be calculated as 1 by 1 minus t square. And subsequently, you can calculate the mean and variance also. So anyways, I can see that the problem has already been solved for you. So you can take a look at this particular problem whenever you'll get time. And then in the, yeah, it has already been solved for you. So whenever you get time, you just have a look at this. And then you can go back to the John Freund book and find out the chapter, the moment generating function, and try to, lots of problems, lots of probability functions are there, lots of problems are there. You can try to calculate the moment generating function of those probability of those random variables, and consequently the mean and variance. This chapter is very important from practical point of view. I'm not sure, I don't know whether I'm able to convey the importance of the moment generating function to you or not. Maybe yes, maybe not, I don't know, because we are in a position that we cannot discuss one-to-one. I cannot see the students' face. If they don't understand something, then they make a kind of face like this, and that we are not able to see it. We can only guess that probably you are understanding. If you're not, if you have any doubt, you can anytime call me. I'm always available. Okay, or you can WhatsApp me. If I can reply in WhatsApp, I'll try to give the reply in WhatsApp. If I think that the question you have asked me requires some sort of discussion, I'll call back. So try to solve. I'm not asking you to solve all the problems from the book. I'm asking you try to solve as many problems as you can. Okay, so understanding of the problem, mathematical thinking of the problem, calculation, comfortability with the calculation, all these things are actually required in the course of mathematics. Okay, that will be helpful for you. Anyways, with this, I'm going to conclude my today's class, with today's session. We're going to meet again tomorrow with something. I have not yet decided what, because apart from taking the class, you have to consider the time frame, which is also limited, and we have to cover the syllabus within that time frame. Okay, so all the best and see you tomorrow. Till then, bye.